Awesome. So hi. In this presentation, we're going to talk about Slack DNSSEC Rollout and a very interesting outage that we had on September last year. So first of all, my name is Rafael Elvira. I'm a staff software engineer on the traffic team at Slack. And traffic team at Slack looks after ingress load balancing, TLS and SSL, CDN, DNS, and DDoS, and those kind of things. So yeah, I'm going to pretend to be a DNS expert during this talk, but I'm really not. So bear with me. Let's go. So first, I'm going to try to get an impression from the audience, asking a few questions. So how many people here, raise your hand if you have an idea of what DNSSEC is? Awesome, nice. And how many of you have played with DNSSEC? Cool. How many of you have deployed DNSSEC in production? OK, good bunch. And how many of you have suffered a DNSSEC incident? Nice. OK. It's not just me. Awesome. OK, so let's dive into what DNSSEC is then. DNSSEC is a set of extensions intended for securing data exchanged by the DNS protocol. So the protocol provides cryptographic authentication of data, authenticated denial of existence, and data integrity, but not confidentiality or availability. So these are the record and key types used by DNSSEC, and I'm going to be referencing on to all of them later on as we move forward. So first of all, the DS record. This is the delegation signer, and it's used to secure delegations between name servers, and it's also referenced as the chain of trust in DNSSEC. Then we have the DNS key record. So DNS key record is the public key portion of the key, and resolvers will use this to verify the DNSSEC signatures in the SREcon records, which is the next record. So SREcon holds a DNSSEC signature for a record set. So that's the junction of a record name and a type. And resolvers will use this SREcon record to verify the signature stored in the DNS key record. And then we have NSEC and NSEC3 records, which are typically used by resolvers to verify the non-existence of a record name and type. So record name might be foobar.com, type might be CNAME, A, whatever. So then in terms of keys, we have the zone signing key. So this is the private portion of the key. It will digitally sign each record set in the zone, while the public portion, the DNS key, will verify the signature. Then the key signing key will sign the public key exclusively, so that's the DNS key, and it will create an SREcon record only for this DNSSEC key. So here is what a successful DNS record request will look like. So it's a basic request where the user will make a request to the recursive resolver of choice, and then the recursive resolver will then attempt to track down the DNS record, and it will do so by making a series of requests, first starting with the root name servers. So the root name servers will point it to the TLD name servers. In this case, we're querying for slack.com, well, app.slack.com actually. And it will point it to the .com name servers. Then the .com name servers will point it to the authoritative zone for slack.com. And then we will try to find the actual record type. So this is a very basic interpretation of what a DNS record request will look like. And the sequence is the same when the resolver does the DNSSEC validation, while the only difference is just the difference in the records requested and returned to perform said validation. So something that we need to keep in mind, and you'll see the green box there, that's the zone that DNSSEC protects, and I say protects with quotes, as it only validates that the DNS response received by the recursive resolver has not been tampered with in transit. So that's between the recursive resolver and the authoritative zone. But bad actors can and will still be able to tamper with this request between the recursive resolver and the client. So now that we've briefly touched base on what DNSSEC is, let's go through our journey at Slack. So back in May 2021, we started off by doing a proof of concept. And in here, we replicated most of the DNS use case we had in our zones on a controlled and isolated environment. And basically, in this environment, we created multiple tests where we gained knowledge on how to operate DNSSEC, because this was a new thing for us. And then once our proof of concept was completed, we worked on an internal RFC, where we outlined all the necessary work that we had to do prior to enable DNSSEC and to enable DNSSEC on all Slack domains. So prior to enabling DNSSEC, we spent a bunch of time simplifying our DNS setup and making some necessary zone changes in preparation for DNSSEC. I'm not going to be covering those today, but if you want to chat about this, just let me know later. So once we deemed our zones to be ready for DNSSEC, we started with the actual, what does the rollout plan look like? And by design, DNSSEC can only be enabled on a per domain basis. So that makes it impossible to enable DNSSEC on a subdomain or subzone. And this design choice will significantly increase the risk of a DNSSEC rollout. So to overcome this, we categorized all the domains by their risk, so low, medium, high, depending on how critical they were for us. And in this way, in case of a failed attempt, especially or bugs on the early days, we would just catch those problems on domains that are only used for monitoring or other non-critical or less impactful Slack features. So as you might have already guessed, Slack.com was the very last domain on our DNSSEC rollout. And prior to Slack.com, we rolled out DNSSEC to all other Slack public domains successfully with no internal or customer impact. But obviously, Slack.com had to be different. So yeah, in this section, we're going to cover the 3 times we failed to roll out DNSSEC to Slack.com. So September 7th, 2021, more than a year ago, we do our first attempt to enable DNSSEC signing on Slack.com. And however, prior to publishing the Slack.com DS record at the registrar, which is the very last step on a DNSSEC rollout, basically when you publish this DS record to the registrar, it will just propagate the record to the .com zones, which makes it effectively all the recursive resolvers will start validating all those DNS requests. So when we do that, before publishing the DS record, a large ISP in the US has an outage, and many of our customers start reporting problems accessing Slack and resolving DNS. So very early in that incident, we decided to roll back the changes before we even know this was an ISP issue. But out of precaution, we wanted to roll back. Then one day later, on September 8th, we enabled DNSSEC signing again, Slack.com zone. We enable signing on the authoritative zone, on the subdelegated zones, and we follow the same procedure as yesterday. But prior to publishing the DS record again, our customer experience team reaches out to us and says, hey, there's a small uptick of customer tickets, and users are reporting DNS resolution problems. So we halt the rollout, and we start investigating what's going on. And at that point, we realized that most of the affected users are accessing Slack through a VPN provider. So once again, we decided to roll back the changes and figure out what's going on. So we put our detective hats again, and we investigate for a little bit. And it turns out that some resolvers become more strict when DNSSEC signing is enabled, even if it's only enabled in the authoritative zone and not, they don't have their DS record published. So this strict DNS spec will reject the CNAME record at the apex or root of a zone, including the apex of a subzone. So if you have Slack.com and you subdelegate app.slack.com, for instance, if you have a CNAME record for app.slack.com in your subdelegated zone, that's included. So this was the reason that customers using a VPN provider were disproportionately affected, because some VPN providers will expose this behavior. So after migrating all the CNAMEs at the apex of subzones to alias records, we were ready for another attempt. This is September 30th, 22 days after our second attempt. We're ready. We did some careful planning, and we go and made our third attempt to enable DNSSEC signing on Slack.com. So this image will illustrate how we first enabled signing on the authoritative name server and the delegated subzones, same as the previous 2 attempts. But this time, we thought about leaving a soak time prior to publishing the DS record, as we had seen issues on the last 2 attempts. And after a 3-hour soak time, more or less, we do successful validations. We're very confident that publishing the Slack.com DS record in the registrar is going to work well this time. So yeah, we go ahead and we instruct resolvers to start validating DNS requests for Slack.com. And at this point, we have successfully enabled DNSSEC signing on Slack.com, which is very exciting. And everything was looking great so far. All the manual tests, the external probes, the monitoring, everything was green. And we were very happy to have completed the very last bit of our DNSSEC rollout. But then after a while, things started to look a bit less idyllic. So our customer experience team, yet again, started getting reports for users seeing DNS resolution errors in their Slack clients. So to give you some context, Slack applications are based on Chromium, and Chromium integrates a way to export a thing called the netlog capture. So netlog, this, is an event logging mechanism for Chrome's network stack, and it will help you debug problems and analyze performance. So netlogs are extensively used at Slack, and on the left you will see the DNS configuration for a client, and that is available inside the netlog capture, and you can see the resolvers they're using, if they're using DNSSEC, if they're using DNS over HTTP, and many other things. And on the right, you can see an attempt to resolve app.slack.com with all the relevant information. So during the initial investigation, we see that all the reports were caused by no data or empty DNS responses, but only from some DNS recursive resolvers. So most of which were either a large private corporate DNS resolver or Google's public resolver, that is Quad 8. So we were kind of surprised that if Google DNS was impacted by this, a large portion, obviously, of our user base uses Google DNS, that should mean a much, much larger impact than our monitoring was showing at the time. So given the data we have, we decided to roll back again our changes for Slack.com. And we attempted to do so by pulling the DS record from the DNS registrar, which effectively will remove the Slack.com DS record from the .com zone, trying to just stop the bleeding. So we could later focus on the no data DNS responses that customers reported initially. So, and then after nearly an hour, there were no signs of improvement, and the error rates just remained stable, flat. At that time, we were pretty confident that reverting the DS record at the registrar was sufficient to eventually mitigate the problems. But as things were not getting any better, and given the severity of the incident, we decided to roll back one step further. And believe me, this is a bad idea. So this step further was no other than rolling back DNSSEC signing in or Slack.com and both the authoritative zone and the subdelegated zones. Same as our previous two attempts. So we basically wanted to recover our DNS configuration to the last previous healthy state, and hopefully allowing us to completely rule out DNSSEC as a problem. And the problem here, and it's that false sense of trust in rolling back the zone signing changes that we had from the previous two attempts. While there was a significant difference this time of publishing the DS record at the registrar. So as soon as the rollback was pushed out, things got much worse. So this is an example of a DNS resolution alert. This alert paged our traffic team during the incident. And it says that Slack.com is failing to resolve from multiple resolvers and probes around the world. So if you're on call for traffic at Slack, this is one of the pages that will make your heart rate go up. So to understand at the time, and what we expected was that a DS record at the .com zone was never cached. So pulling it from the registrar will essentially cause the resolvers to stop performing DNS validation. And this assumption turned to be somewhat untrue. As the .com zone will ask resolvers to cache the Slack.com DS record for 24 hours by default. So you're pulling the record, but whomever has it cached for 24 hours. So we knew stopping signing was a high-risk operation unless the DS record was not published anymore, and that's the reasoning why we stopped signing the authoritative zones, because we had this false understanding of pulling the record will essentially just pull it back and it's not cached. So unlike the previous two attempts, this time resolvers had cached the DS record for 24 hours, so all validating resolvers now were starting to return serve fails to all Slack.com lookups. So we quickly realized of the mistake we had just made, and we started contacting major ISPs and public DNS resolvers, just asking them to flush the cached records for Slack.com. We also proactively flushed caches for resolvers that offer a public website, like Google Quad 8 or Cloudflare Quad 1. But as resolvers flush their caches, we slowly saw signs of improvement, but not complete sign of improvement, like we were not healthy yet. So an interesting bit here is that we used our internal monitoring to track this down, and a good bit is that Slack clients send their telemetry to a different domain called slackb.com, and thanks to this isolation, we were still able to collect all those client metrics that would help us quantify the incident and know when things were getting better. And ironically, slack.com had DNSSEC enabled before this incident and during the incident as well. And it didn't show any issues, which is interesting. So throughout the incident, we thought about restoring the keys. So basically re-signing the slack.com zone, but without publishing this DS record at the .com zone. As we thought it would slightly improve the situations for some users, but it wouldn't have solved the issue from the beginning from all those no data responses. And the thing is, to restore the signing, we would have had to recover the key signing key because that was deleted when we rolled back the changes to the slack.com zone. So to give you some context, in RA53, which is what we use for this authoritative zone, the key signing key is managed by an AWS KMS key. So this KMS key is recoverable because we only self-deleted it, meaning that the key signing key would be the same, but the zone, we were uncertain if the zone signing key would be the same or different. As you know, the zone signing key is fully managed by AWS, and we have no visibility into it. So after the incident, we were chatting with the Amazon RA53 team, and they confirmed that the zone signing key would have been different, as when you re-enable signing on a zone, the zone signing key just generated with a new key pair. So meaning all DNSSEC validating resolvers will just continue to fail, at least until the DNS key TTL expires, which is a separate TTL. So we decided not to restore signing as we had a lack of confidence in doing this. And at this point, and some hours into the incident, the situation with Slack, most clients were resolving correctly, but there was a long tail of small users in small DNS resolvers or ISPs that hadn't replied that were still impacted. And then as public resolvers were flushed and the 24-hour TTLs expired, the error rates just went back to normal. And at this point, the only thing we had was a mystery to solve. So once impact to customers was mitigated, we aimed to determine the root cause of this outage. So prior to attempting DNS on Slack.com, our team had successfully enabled DNSSEC on all other Slack public domains. So this brought up a lot of questions, like, how is Slack.com different? Why did we not see any issues with any of the previous domains? And why did it impact only some customer, internal corporate DNS resolver, and some of Google public DNS, but not all of it? So to understand what happened, we basically replicated the rollout steps using a test zone. And we set this up identically to Slack.com. And we used a resolver that we knew had problems during the outage. And surprisingly, all our attempts to reproduce this behavior were unsuccessful. So, at this point, we're like, let's go back to those net logs that we received from customers, and let's see what do we see there. And here is where we find an extremely interesting clue. Clients were able to resolve Slack.com all through the incident up until we stopped signing the authoritative zone, but they were not able to resolve app.slack.com. Why so? So this indicated that there was likely a problem with the start.slack.com record. And this is a wildcard record that we have on our zone. At that point, we thought, none of our zones that we've done DNSSEC before has any wildcard record. So this is clearly an oversight that we had before attempting Slack.com. So we collected all the evidence, and we reached out to the Amazon RA53 team. So we jumped on a call together, and we tried to figure it out. And after walking them through all this evidence and the findings, they quickly correlate this behavior to an issue with NSEC responses that RA53 generates on wildcard records. So they're like, we have a ticket for this on the backlog, so maybe it's that. So basically, when a request is made to a DNSSEC-enabled domain for a wildcard record, which type doesn't exist, for example, a quality record for IPv6, the answer is a signed NSEC record that confirms that while the domain name exists, the type does not. This NSEC response can include some additional information that is specifically there to not break wildcard records. But in this case, RA53 was not returning this additional information at all. So what this means is that when a client does a quad-A lookup for app.slack.com, it will correctly return a signed NSEC saying there is no record for that, And this is correct, since we don't publish any quality records. But then the expected behavior is to fall back to requesting an A record. But since RAF53 isn't returning that extra information, some public resolvers will take this response to mean no other record type exists, and there's no need to query for an A record. So this NSEC response obviously comes with a TTL, so it will be cached by DNS resolvers, meaning that impacted resolvers were innocently or unintentionally being cache poisoned by this response. So luckily, this cache poisoning specifically only would affect the regional cache of Google public DNS, which means that only users of an impacted regional cache would be affected, while other regional caches would not. So this essentially means that if someone in the Amsterdam location, if there's one, would query for a quality record, only users connecting to that location for Google public DNS would be affected as well, but others not. So once we knew this, we were able to reproduce this issue in our test zone against Google DNS, but not against Cloudflare DNS, for example. So there was a second mystery here, whether one or the other of these major public resolvers was out of spec. So we go back to reading DNS RFCs, and we figure out that it is protocol compliant to reuse the cached NSEC record to decide a subsequent response. So this is called recursive NSEC, which is an optional spec that Google DNS implements, but Cloudflare does not. So in the end, we concluded that both options were acceptable. And the only real way to avoid being in this ambiguous situation is for the authoritative name server to correctly return the record type and the NSEC bitmap, that additional information from the NSEC record. So yeah, at this point, our mystery is finally solved. And once we figured out what had happened, we just went and wrote an extensive incident review document. We just tried to figure out what the incident remediations items were out of this, and we worked very closely with RAF53 to fix the bug and also make the zone signing key recoverable in case this happened again by accident. We also spent some time writing a blog post for our engineering blog, which is basically a written down version of this talk, and there's some key takeaways there and a way to explain to the community what happened here. So after all of this, we started planning for the next attempt number 4, with the hope that this attempt would be the very last one. So this is the last status update in the DNSSEC project channel. This is a few days prior to attempt number 4. And I think this list is quite interesting, as it shows the various focuses that we had when planning for one of these attempts. So first one I would say is documentation and testing. We focused on writing really good runbooks that were very methodical and that were proven to work on test zones. So runbooks for rolling out DNSSEC, rolling back different cases, and whatnot. We documented and we tested zone signing key restores. So actually, test and prove that the zone signing key restore feature that RAF53 worked for us worked. And we did the same for the key signing key restore. So we basically we grabbed this test zone and we broke it in as many ways as we knew, and we tried to recover it from its bad state. The second focus was observability, I would say. We worked on additional logging on our DNS traffic. So there's an interesting feature in RAF53 that's RAF53 logs. So if you enable this, it will stream your DNS traffic into CloudWatch metrics, which you can turn into CloudWatch logs. And in there, you can see drop traffic by resolvers. We can see patterns by resolvers. We can see when resolvers start asking for DS records, which essentially means they're starting to do that DNSSEC validation. We can see serve fails and many other things. So we basically plotted all this into a dashboard, and we kept it in a screen while we were doing the rollout. Then another thing we focused on was communications. We communicated widely both inside at Slack and within Salesforce. We had an open communication with RAF53, both before, during, and after the incident. And we sent some communications to mailing lists. So there's Nanogy. If you don't know it, it's the North American Network Operation Group, and DNSORC, which is a DNS operators community. So we did this just for awareness. Both of these communities really helped us during the incident. So there's a lot of folks there that look after networks and could help us in case of a bad rollout. And then in terms of rollout plan, we just agreed to stick to the runbook. Follow the runbook. We know this is what it works. It's very easy to break DNS or DNSSEC in particular. So we know that the steps in the runbook are what work, and we should be true to that. We also did some zone changes as well. So before enabling signing in this case, and to reduce the impact if things went wrong, we just reduced a bunch of TTLs, including the SOA minimum TTL, just to reduce the impact of anything going wrong. So the fourth attempt was finally the charm, and today Slack.com has had DNSSEC enabled for, I think, nearly a year with no reported issues at all. So yeah, before we jump into Q&A, I want to do some acknowledgements. And yeah, I would like to thank the Rafael team. Their collaboration with the fix was really good. The Salesforce Public DNS team, they were very kind. Their support and their DNS expertise really helped us during the incident. And essentially, all the DNS community was really helpful during this. So I would like to thank them. And last but not least, our huge thank you to our customer experience team. They're the ones in the front lines every day, connecting the dots between customers and our engineering teams. So we really could have not done this without them. So yeah, feel free to go ahead and give a read to a more detailed write-up about this. It's in our engineering blog at slack.engineering. And yeah, I'm now ready to take any questions you might have. Thank you.